The desire of printing faster has gained a lot in popularity over the past 2 years. A lot of water has gone under the bridge since the day I decided to print as fast as my printer could take it. 800 mm per second seems pretty slow, now that we're looking at reaching out to the 2 meters per second milestone. Acceleration, power, light mass, there are no secret in moving this fast. Getting the material melted fast enough to support such craziness is now the next struggle. We have access to a very wide selection of hot ends to serve our need for speed. But which hot end is the one you really need? From this very wide selection, it can be quite confusing to select the hot end that will be the right one for your printer and for your needs. Some hot ends will focus on flow, others on lightweight, small form factor, easy maintenance, and a lot more characteristics. To help you in this selection process, I am proposing today a series of videos in which I will try to identify and quantify the characteristics by which we could evaluate every hot end available in the market, and perhaps future ones also. These evaluation points should tell us more about which hot end is right for your needs. For this very first episode of the Hot End Olympics, I propose that we have a look at the testing methodology and the results format. What better test candidate than the E3D V6 hot end as our guinea pig to understand and baseline each test? Let's have a look at the test rig. The installation is fairly simple. A 24-volt power supply feeds a Duet Wi-Fi control board running Clipper. The Raspberry Pi obviously is required for Clipper, and we have right here a Bondtech LGX as the extruder. That goes for the easy part. Then we have measuring devices. The first one is a rotary encoder to measure the amount of filament going into the hot end. Then we have right here a very precise pressure sensor that will be measuring the force at which the filament is being pushed into the hot end. The entire hot end assembly is mounted on a hinge with very limited friction for accurate readings. Both sensors' readings are then being captured by an Arduino and fed to the Raspberry Pi to be logged along with the nozzle temperature in a data table. Not only will it define the maximum flow under manageable pressure levels, but this test rig will also reveal stuff we never thought of or did not even believe was actually happening in our hot ends. Because we also need to move this entire system around the X and Y coordinate plane, we will measure its weight as well as the distance between its center of gravity and the point of fixation to the print head. With all this data in hand, it should become much easier to compare hot ends between each other. Just like one of my favorite shows did many years ago, a ranking chart will be putting the winner of this competition to the top while welcoming new contestants at each episode. So let's try this testing process with our guinea pig, the E3D V6. The V6 hot end has been E3D's flagship hot end since 2014. Affordable, efficient, and reliable, this configuration has established a standard within the industry. Any other company offering hot end product or parts had to be compatible with the V6. Nozzles, heaters, thermistors, heat breaks, pretty much every aftermarket parts available today is compatible with the V6. Is the V6 still a good candidate for speed printing? Let's find out. The unit we're going to be using today is a pretty used unit. It has served me well on my Hypercube Evolution for years. It is equipped with a standard 30-watt 24-volt heater cartridge and a titanium heat break. We will be testing its performance sporting a 0.4mm nozzle as well as a 0.8mm nozzle later on. Before we start with performance testing, let's review the physical properties of this unit. All loaded with the heater, the thermistor, and some wire length, our V6 weighs just short of 42 grams. Adding the fan and shroud brings us to 56.9 grams. It has a length of 62.5 millimeter, and the melt zone measures 17.5 millimeter from tip of the nozzle to the throat of the heat break. The heatsink is pretty long, with plenty of cooling area within its fins, and the big 3010 fan helps a lot with cooling. The heater block is made from aluminum and is retained by the heat break only. The heater cartridge is perpendicular to the melt zone, and the melt zone is located between the heater cartridge and the thermistor. This ensures accurate readings of the nozzle temperature. By using this small jig, we'll be able to find the center of gravity of our assembly. Finding the center of gravity will help us in establishing the moment of force produced by the application of the assembly's weight on the lever defined by the distance between the center of gravity and the mounting point to your print head. The moment value obtained in Newton centimeter will give us a good basis for comparing hot ends between each others. This assembly has its center of gravity at a distance of 35.7 mm from its mounting point. Multiplying this distance with the weight of our assembly, we obtain 2030 gram-millimeter. Then converting grams to Newton and millimeter to centimeter, we obtain 1.99 Newton centimeter. This means that under a 1g acceleration from back to front move on the y-axis, oops, sorry about that. I should remember that I'm talking to a 3D printing audience. Let's start that over. So this means that under an acceleration of 9,806.65 mm per second square on the y-axis, the V6 will apply a rotating force of 1.99 Newton centimeter on its mounting point. You can now easily understand that if we increase the weight or increase the length of this assembly, we also increase the twisting forces applied to your print head, resulting in potential artifacts on corners and sharp edges during fast printing. And now, here comes our main course, the flow testing. The test plan is to make an extrusion run on the test rig for every 10 degrees Celsius increment. The extrusion rate will be increased progressively during each run until the extruder skips steps or when the filament will start slipping. Along with the quantity of material being extruded per second, the pressure sensor is recording the amount of force utilized to push the filament inside the hot end. Additionally, because I'm a bit crazy, and you should know that by now, and I also have way too much time under my hand, wink wink, I feel that I should also design a print head for each hot end and validate the maximum flow with actual printing. And yes, for each material and each of the two nozzle sizes as well. The test rig conditions could be misleading under some circumstances, and we'll see why later on. The actual printing is going to help us clear that out. I am reusing the pattern from my good old friend Vez 3D for this test. While this pattern maximizes the amount of straight lines on the same layer, it also limits the amount of flow disruption from sharp cornering, and it also allows each layer to cool properly. Thanks, Vez. The print speed will be increased at each layer until the print quality becomes unacceptable. The same type of rotary encoder as on the test rig is also going to be used to record the actual amount of filament going through the hot end. By comparing the amount of filament requested by the G-code and the actual amount measured by the encoder, we already have an idea of where the breakpoint will be. Unfortunately, I did not find a way to mount the pressure sensor on the print head without obtaining too much noise and unreliable data due to the hot end swinging around under hard acceleration and direction changes. So this is something to keep in mind when we will review the data. I really wanted to test the maximum flow during actual printing to resolve a few questions that I have. Can we still print properly at the ultimate maximum melting capacity of a hot end? Will the increased pressure inside the hot end caused by the printed part partially obstructing the nozzle contribute at augmenting the melt zone height? And is there a pulling effect from the filament getting grabbed by the material previously laid and therefore helping it in getting out of the nozzle? I don't pretend to have all answers to these questions yet, but I'm convinced that the observations that we will be doing during these Olympics will greatly improve our understanding of what's really happening in our hot ends. I will focus on these topics into additional videos that will be published between the various episodes of the Olympics to further explore or explain some of the observations made during these tests. Make sure to subscribe and hit the bell so you don't miss any of these findings. Time to grab a coffee and wait for our first test run to be completed. We'll be back right after this. Alright, glad to see you back. Now that our test rig and printer are calibrated, that the test environment has been documented, we can dive into our first results analysis. Let's see what the V6 using a 0.4mm brass nozzle can give us when using PLA. There is a lot of information on here, so it can be confusing at first. Let me break this down into pieces for you. The bottom axis represents the material flow in terms of cubic millimeter per second. On the left axis, we have the amount of pushing force applied to the filament. This force is expressed in terms of newtons. On the right part of the graph, we have a second vertical axis. This one represents the average temperature deviation between the targeted nozzle temperature and the actual measured value. The pink dotted line here shows this temperature deviation in relation with the flow obtained. The dip at the beginning is normal. It is simply due to the fact that the nozzle temperature was stabilized at the targeted value before the test started. We can then see the controller board trying to maintain that value as stable as possible using its PID algorithms as we push more and more filament. It tends to keep the temperature slightly under the target, probably because we are constantly increasing the flow of material to be heated up. The oscillation at the end indicates that the heater has a hard time to keep up. The PID tune is probably not optimal for this flow, and the dip at the end probably indicates that we are outrunning the heater's capacity. Let's turn on the test sequence performed at 220 degrees Celsius, which is a pretty common printing temperature for PLA. As we increase the amount of filament pushed, we can see that the force applied by the extruder on the filament is also increasing. This means that the pressure inside the hot end is increasing as well. So far, we have a pretty linear pattern, which indicates a stable and predictable situation. And see what happens when we try to increase the volume of filament pushed furthermore. We're reaching to a point where the pressure starts to climb much more rapidly, until we have an almost vertical curve. If we were to try exploiting this range of flow at this temperature on this hot end, we would get an erratic extrusion flow very difficult to be properly predicted, therefore throwing out of whack your retraction and pressure advanced settings. And this is without speaking of the potential mis-extruding caused by the gear slippage and the stepper motor failure. This range of pressure might also result into non-uniformly melted filament output, like we can see here while using ABS at overcapacity. Now that we understand our pressure profile for this configuration, let's bring the real-life printing results. By measuring the last height of our test profile that printed correctly, we can then pull the readings from the rotary encoder. It is too bad I couldn't find a way to obtain reliable data from the pressure sensor when mounted directly on the print head, so we will simply report the maximum printing value on this graph, knowing that the pressure profile might be slightly different when printing for real than what it showed on the test rig. So at this temperature of 220 degrees Celsius, the last layer that printed correctly corresponds to a printing flow of 14.3 cubic millimeter per second. This maximum printing flow value corresponds directly to the area of our test rig curve where the pressure was starting to creep. This means this testing methodology might be working after all. Haha. The rest of the curve from that point on will be dashed to indicate the non-printable zone. Let's turn back on the other test sequences done at other targeted temperature values. What a cool graph! More than 250,000 data points were used to create this image. Crazy when you think about it. I would like to thank the Exodus and Lixbox from the Clipper Discord server for their help in programming the tool that allowed me to do such capture efficiently and precisely. Thank you very much, guys. So let's have a step back. What can this graph really tell us? It is clearly visible that more heat will increase the allowable maximum flow of our hot end. Given that we can cool properly the filament after being extruded, we could gain a lot by printing hotter. But be careful. Printing a material at hotter temperature than the value recommended by the manufacturer could mean two things. First, you'll start to get more undesirable toxic fumes. And second, you'll potentially be degrading the physical property of the filament. This could mean weaker parts. The pattern traced by those maximum printing flows reminds me of something. Do you see it as well? Yes, the max torque per RPM for our little NEMA 14. We could potentially be able to obtain a bit more flow for this filament by using a stronger stepper motor. But then again, the gain wouldn't be much as the pressure creep zone is still around the corner for every single of those points. Because we need to pick one value for our wall of fame, we will use the flow obtained at 220 degrees Celsius, which is the maximum recommended temperature for this PLA. Along with the maximum flow, this wall of fame will also list the physical properties of each unit. This way we can easily compare all hot ends based on different factors. Our V6 using a 0.4mm brass nozzle has a total weight of 56.9 grams. The center of gravity is positioned at a distance of 35.7mm from the mounting face. This produces a moment of 1.99 Newton centimeter. A maximum flow of 14.3 cubic millimeter per second was measured via actual printing using filament.ca EcoTough natural color PLA at 220 degrees Celsius. I will take a stab at creating an index using the maximum flow divided by the moment. This index will be used to compare and rank hot ends between each other by considering their physical properties as well as their maximum flow capacity. It might not be the best way to do it, but we will readjust as required along the way of these Olympics. Having the data in hand gives us such flexibility. Please remember that I'm learning just as much as you guys in this adventure. Let's stick with PLA for a moment and see how a 0.8mm nozzle will affect the results. Although the pressure curves from the test rig are shooting through the roof of flowing capacity, the actual printing maximum flow is considerably lower, just a little bit more than what we got with our 0.4mm nozzle. The explanation for such difference between mid-air extrusion and actual printing results is caused by cold core extrusion. What is that? Well, when reaching a certain pressure level inside the nozzle, it will become easier for the unmelted center of the filament to simply deform, stretch, and then squeeze through the bigger nozzle hole than it would take to block the nozzle and create enough restriction and pressure to eventually stall the extruder motor. We can observe and confirm this phenomenon by measuring the filament after extrusion. The filament gets swollen right after exiting the nozzle. This 1.58mm extruded piece was created using a 0.8mm nozzle. There is definitely an elastic motion happening here. Another way to observe that phenomenon is to look at the cross-section from one of these swollen extrusion. See the different texture from the center of this piece compared to its surrounding. For this reason, it became clear to me that actual printing was required to establish the real flow capacity of a hot end. I have used a line width of 1mm and a layer height of 0.48mm with this 0.8mm nozzle. There might still be some of that cold core extrusion phenomenon happening, but I evaluated this to be minimal since we are within reasonable range of the results obtained with the 0.4mm nozzle. Now let's see how changing filament material affects the results. This is now ABS, a completely different pressure profile for this material. I could not get the test print to work below 220 degrees Celsius with the ABS due to bed adhesion issues. This is why the lines are completely dashed for the temperature curves below that point. Although we can see that ABS pressure progression curves are smooth and much more regular than what we saw with PLA, there are some things I cannot explain yet. Like these spikes repeating through several test runs when using the 0.8mm nozzle. They might be related to the cold core of the filament making contact with the taper surface of the nozzle. If you have hypotheses that could explain these behaviors, please leave a comment here below. I'm eager to read these results through a different eye. We will use the maximum printing flow at 260 degrees Celsius for ABS. So using a 0.4mm nozzle, our V6 has a throughput of 15.1 cubic millimeter per second. And when using a 0.8mm nozzle, this maximum printing value becomes 17.2 cubic millimeter per second. Last material, PETG. PETG is perhaps the more flexible and elastic filament from the three we are using in these Olympics. The pressure curves are pretty different from PLA and ABS. I suspect the more erratic and harsh texture of the curve is created by the filament taking the shape of a snake or a coil in the hot end under the push from the extruder motor. I could be wrong, but this is the only thing that makes sense to me right now. Because we can only use one temperature value for our wall of fame, we will capture the maximum flow at 250 degrees Celsius. This is the temperature that I found to work best with this PETG 3D fuel filament. So we will grab a 13.3 cubic millimeter per second for this 0.4mm nozzle using PETG, and we will use 18.7 cubic millimeter per second for the 0.8mm nozzle. Do you see the bigger difference between the results of those two nozzles? Could this be related to using a more elastic material? How are these results talking to us? How will we be able to compare hot ends between each other using this table? Once again, I don't have the answers to all these questions yet, but I am sure that as we go through these Olympics, we will learn a great deal about what is really happening in there. I would like to take this opportunity to thank all suppliers who have sent me an example of their precious design to be tested. It's been over a year in some cases, and I feel quite bad about it. But I wanted to do things right. This project has quickly grown out of proportion. I believe the results should be worth the wait. If you would like to support my work and help me covering the various fees involved in creating such a video, I invite you to donate a few bucks through the PayPal link in the description here below. Thank you very much for your precious time. I hope this data will help in moving the open source community forward. Who knows, perhaps one day we will be printing with hot ends lighter than the tip of a pencil that have a maximum flow of over 100 cubic millimeter per second. Until then, see you soon on the next episode of the HotEnd Olympics.